All right, welcome back, y'all, to our last week. I'm super excited to talk about geometry with you. There's kind of a lot here, so I'm going to do a quick overview, and then I'll probably make a separate video where I do more of the practice problems. So these are just helpful reminders because it's probably been a minute since you've taken geometry, and a lot of these topics are really niche, really specific, and so sometimes you see them on the SATs, sometimes you don't, and that kind of sucks because it's like, do I need to know it or don't I? All right, so let's dive into it. Kind of the first topic we touch on in geometry are just lines and angles. So we have this segment addition postulate thing, which postulate sounds super fancy and stuff, but basically it just means if I have a segment broken up into pieces, like two pieces, then I can add those two pieces together and they equal the whole thing. Now, I have this word bisector and midpoint down here, which also has to do with line segments, but it's a little bit more specific. So generally, if you have a line broken up into pieces, you can add all the little pieces together to make up the whole line. I think that's pretty obvious. Angle addition is similar, except for now you're looking at an angle that has a ray cutting into it. And normally, we name angles with 3 letters, but just to be a little bit simple here, we'll call that angle 1 and this angle 2, and then the whole angle ABC. So angle addition does a similar thing. If I have a big angle and it's broken up into pieces, I can add up the pieces, so angle 1 and angle 2, and it will equal the entire angle, so angle ABC. Again, probably by now some of you are like, why did I ever think that this was tricky? And then we have some special angle pairs. So if it's not just a general angle, if they tell you that it's a specific type of angle or they've marked that it's a specific type of angle, you can do certain things with it. So if they tell you that you are supplementary, that just means that the angles will add up to equal 180 always. Now, I did not come up with this trick, but somebody showed me this trick once, and I wish I had seen it when I was in high school because I always got supplementary and complementary goofed up. But your sup only almost makes an 8, and 180 has an 8 in it. So maybe that's a good way to remember if you don't. Complementary, the other one, are angles that add up to equal 90 degrees. And I guess the way to remember here is you can take the C and kind of drop it down and you get 90 right there. I thought that was kind of cute. Helped me remember. And I've just been doing it for so long, I remember now too. And then another type of special angle is actually a vertical angle pair, which vertical feels like it should be up and down. And it is, but it's also this way as well. These angles are congruent to each other or the same measure, and the top and bottom angles would be as well. So vertical angles are equal. So angle 1 equals angle 2. So instead of adding up, I put one angle on one side, one angle on the other. They're equal to each other, and I can solve for things. Now, as I said before, midpoint and bisectors are things that you attribute to lines or angles. So I can be a midpoint of a line. So that means that that line has basically been cut in half. Each side of the line is equal. This would be my midpoint right in the middle. And you can do lots of things with that. You can set each piece equal, or if you know the entire line is 10, you can take half to get either side, so 5 and 5. Or if you know the smaller half is 7, then the whole thing is 14. So lots of different things that you can do there. Now you can also have a bisector of a line segment, but typically a bisector is a line that cuts through another line. So, but also right in the middle. So maybe I have this line here that's cutting through this little line segment. And again, either side is the same, but I don't necessarily know anything about the bisector itself. I don't know if that thing was split in half. It's just splitting the line it's going through in half. So, and you do get a point right there that you could call a midpoint, but a bisector is more like a line or something like that, or a ray. Which leads me to the next point. I can bisect an angle as well. So like if I have an angle and they've told me that this ray is the bisector, then again, I know that either side is the same. And you can do lots with that. Again, you can set either side equal to the other side. Or like if you know the entire angle is like 100 degrees, then each one is 50. Or if you know that the smaller piece of the angle is like 20 degrees, then the whole thing is 40. So you can double or take half or set each side equal. And then lastly, when it comes to kind of angles and lines, we eventually in geometry get into parallel lines. So just like parallel lines hanging out in space, not on a coordinate grid. And if you cut it with a transversal, you get a whole bunch of angle pairs. So like we get a supplementary pair, which can also be called a linear pair if they make a straight line. We get vertical pairs, but the moment we start jumping from this crossing to this crossing, so like traveling along that transversal, we start getting other angle pairs. So like corresponding angle pairs, alternate exterior angle pairs, alternate interior angle pairs, same side interior, which add up to equal 180. And did I get them all? Alternate interior, alternate exterior, corresponding. Yeah. Now, you probably don't need to know the names of them. You can probably just look at the picture and be like, yep, those look equal. Or no, they don't. And if they don't, then usually that means they add up to equal 180. So, all right, moving right along. The next thing that we come to in geometry is triangles. We're in triangle land for a real long time, and you got most basic triangle sum theorem. That's where the three angles in a triangle add up to equal 180. You also have this exterior angle theorem where like basically if you have a triangle with a little tail, that tail outside angle right there will always add up to equal the two inside ones. So if we call this angle 1 here, angle 1 is equal to the two star angles being up. So the outside angle is equal to the two non-adjacent inside angles together. We got special types of triangles. We got isosceles triangles, where two sides and two angles are the same. We got equilateral or equiangular, which is three sides and three angles the same, which means that your angles will always be 60 degrees, which 180 divided by 3, hopefully that makes sense. You also have scalene, which is not super special, but scalene is where they're all different, so like I'm not going to write it. We also can find the area of triangles, although I feel like I should have put that down with all my other area stuff, but oh well. Area of a triangle is half base times height, and I'm pretty sure that that is on your formula sheet. Probably not that you need it. We talk about congruent triangles in geometry. So in congruent triangles, all of your angles need to be equal to each other, and all of your sides need to be equal to each other. However, we kind of learned some shortcuts. So like, I don't necessarily need to know that all of the angles and all the sides are equal to be able to say that triangles are congruent to each other. But once they are, then all of the pieces are. And some of the shortcuts that we had is like side, side, side. So I would know that two triangles are congruent to each other if all of the sides of one match all of the sides of the other. Or side, angle, side. So like two sides and then the angle in between match two sides and the angle in between of a different triangle. Angle, side, angle, and angle, angle, side. We also used hypotenuse-leg theorem, which is specifically for a right triangle because right triangles have hypotenuses. And the thing is with hypotenuse-leg theorem, if you think about the marking of it, I have to have a right triangle. My hypotenuse is congruent to another hypotenuse, and a leg is congruent to another leg. And like the little acronym that we would use here for like side to side, side angle side or whatever would be angle side side. So That's why you don't use that. And normally we can't use angle side side to prove general triangles are congruent. However, if that triangle is a right triangle, because of the Pythagorean theorem, hypotenuse-like theorem works. So, and then we also talk about similar triangles. So in similar triangles, all angles are equal, but the sides are proportional, which just means that like they're related by a certain scale factor. So like maybe they were all blown up by 2, or maybe they were all scaled down by half. But sometimes the scale factor is not so easy. So generally the way we find scale factor is we put like one triangle side length over another. So like writing a fraction here. So like a side of a triangle AB over the side of the other triangle DE. And they should all be the same. So like if I go to a different side on the same triangle, it should be the same fraction as the first. And so if you have 2 fractions equal, that's proportional. But then the third one should be the same as well. And that just helps you solve for things. Like if you know this triangles are similar, they'll have a certain scale factor. I always choose which triangle I'm going to put on top of my fraction and then put the other triangle on the bottom. And I try to set up these fractions so that I can do cross multiplication and solve for things. So, okay, moving right along. Leaving the land of 3 sides and jumping into multiple sides. We have polygons. So the polygon sum theorem, I feel like this is also maybe a formula that they put on that little formula sheet for you, but it's n minus 2 times 180. That will get you the sum of all the angles inside of a shape. So like if it's an octagon, I would do 8 minus 2 times 180, which is 6 times 180, which is something, I don't know. If I want to find just one of those angles when it's regular, and regular means all the things are equal, like all the angles and all the sides are equal, I can take the sum and then just distribute it evenly between all the sides, so that, or just sides, angles. So then I'll have the measure of just one of those angles. We can also talk about the outside angles. So like if I do have a cute little hexagon, I'm not going to do an octagon, that's too many sides. I can get exterior angles as well by like extending all the sides. You get a cute little pinwheel thing, but all these outside angles will always add to 360 degrees. And again, if I'm regular and I want to find just one, I can do 360 divided by n, so like split it equally between all the angles. Or really, your exterior and interior angles make a linear pair or are supplementary, so like they'll add up to equal 180. So that's also a fun fact that is helpful. And then lastly, if I want to find the area of any polygon at all that is regular, so all the stuff's the same, we can do half apothem times perimeter. And then I believe that they give you most of the area formulas of shapes that you would need. So like a parallelogram and a rectangle and a square would be in there. So, and then we talk specifically about just quadrilaterals for a while. And so kind of the hierarchy or like family tree of quadrilaterals is you can either be a parallelogram, a trapezoid, or a kite. And the way we differentiate is between how many pairs of parallel sides. So this has 2 pairs of parallel sides. This has 1 pair of parallel sides, and this has 0 pairs of parallel sides. And so if you have 2 pairs of parallel sides, you're a parallelogram, but you might be better than that. You might be a rectangle because you have all congruent angles. They're all 90. Or you might be a rhombus because you have all congruent sides. Or if you have both those features, then you're kind of like the baby of rectangle and rhombus because you have daddy rectangles traits and you have mama rhombus traits, and so you're baby square. That's kind of how that works. Has all congruent sides and all congruent angles. Now, if you're a trapezoid, you only have one set of parallel sides. The other ones can be like, so probably a trapezoid that you're thinking of is like this. You can actually be slightly better than just a plain old trapezoid. You could be an isosceles trapezoid, which just means that these legs are the same. So two sides the same, not the parallel ones. Or, kind of didn't leave enough room for myself here, you could be a right trapezoid, which just means that like one side is 90, but the other side isn't. So like the non-parallel sides again come to a 90-degree angle. But if the other one did, then you'd be a rectangle. So it ain't that. And then if you're a kite, that just means you're a kite and you don't have any pairs of parallel sides. Although a kite is a little bit special because it does have perpendicular diagonals. There are a lot of diagonal features with parallelograms, just like too many to remember or remind you of right now, but we might get to them when we do some of our practice problems. Oh my word, then we have circles. Oh, and they're not my fave. Circles are so specific and like so small. Like, and I don't mean that in a negative way, but it's just like sometimes you'll see a circle problem on the SAT and I feel like most of the time not. And that's unfortunate because there's so much stuff with circles. So I'm going to try to do this quickly and just give you the basics because there's a lot of weird stuff that you can do with circles. So if I'm trying to find the radius, that is like half the diameter. So it's like center to side. I mean, if you can call the edge of a circle a side, I mean, let's just go with it. The diameter is 2 times the radius, or 2 radii. Or it goes side to side, but through the center. So side to side, but through the center. Like it must go through the center. Now a chord is kind of like a diameter where it connects side to side, but it does not go through the center. So line, segment, side to side, not through the center. A secant is a line that goes like through the edges of the circle, through the sides. So like a chord would look something like, okay, I have a circle, here's my center, side to side. A secant is a line going through the circle. I suppose it could be through the center, but kind of the way that I remembered it is it touches a circle twice, and secant is like second, and second is twice. I don't know. It's kind of a weird way, but basically a secant would look like something like that. So it's touching it once, twice. It enters the circle and exits the circle. And it could go through the center. That would be fine as well. Now a tangent is a line that touches a circle only once. And kind of in a specific way, it kind of like bounces off the edge of it. So like if you're looking at a circle, a tangent line just doots it like right on the edge of it, like real close, just touches it once like that, like bounces off. And then an arc is like part of the edge of the circle. So part of the side or the edge of a circle. So like if I'm looking at a circle here, it's like from here to here. So it's like the curvy part. It's not really a line. It's part of the circle edge. And you can do so many different things with an arc. So some of the things that I think are more common are to talk about like lengths and areas and things like that. So if I'm trying to find the area of a circle, we're doing pi r squared. I know there's another one. It's the circumference 2 pi r. The way I always remembered the difference, you guys, is again, area is always a squared measure. Like if I'm trying to find the area of something, it's like centimeters squared or feet squared or whatever squared. And this is squared and this is not. So that's kind of how I remembered that. A sector is like part of the area of the circle. So it's like a pizza slice of the circle, like how much pizza slice did I get here? And so if I want to find the area of a sector, we're doing x divided by 360 times pi r squared, where x is like how many degrees around the circle I've traveled. So like they'd have to tell you that to find it. So like if this right here was like, I don't know, 60 degrees, then I put that above that. And it's over 360 because 360 is the total degrees. So you're like literally taking a portion of the area of your circle. So however many degrees out of the total is the portion of the area that you want. And similarly, so circumference is 2 pi r. That's like the edge of the circle. It's kind of like perimeter. If I wanted the length of the arc, so again, kind of like a picture like this, how long is this line? I want a portion of the circumference. So again, I do x over 360, where x is how many degrees that arc has traveled times 2 pi r. So again, a portion of that circumference. Oh, and then lastly, I squeezed that in there and then wrote over top of it. If I'm talking about circles in the coordinate grid, getting into some coordinate geometry, we can graph those by doing x minus h squared plus y minus k squared equals r squared, where r is radius, and then h comma k is the center of the circle. And then sort of the last thing that we do in geometry is we find surface area and volumes of three-dimensional shapes. And so the three types of three-dimensional shapes you have are prisms, pyramids, and spheres. So a prism has two flat bases that are like parallel to each other. So think like a jar or like a can or something like that. It could be circular, that's called a cylinder, but just anything with two bases. A box, a pyramid has one flat base. So I mean, like literally think pyramids of Giza. That's a pyramid. What else? Like a cone, so like an ice cream cone, whether it be circular based or square based. Those are pyramids. And then a sphere is kind of like the earth. So it's like a puffed up ball. I don't know, basketball. I'm gonna just say basketball shaped. I don't know why I picked basketball. I don't play basketball. Volleyball. I should have gone with that. Soccer ball. Anyways, I think if they ask you to find any of these, I feel like they would give you the area formulas for them. However, they're not too hard to like just piece together. Like usually you can see all the pieces of your three-dimensional shape and find the area of each piece and add them all together. And that's essentially how we come up with these area formulas. So like for surface area of a prism, we just do 2 times the area of the base, because there are 2 bases, plus the perimeter times the height, and perimeter of the base, because the perimeter of the base and the height kind of gets you the stuff around the shape, like the area around the shape. And then if you're wanting volume, you do area of the base times the height. It's quite literally like you're finding the area of the bottom and then you're just stacking a bunch of little flat pieces. So that's why we multiply it by the height. Like how many of those little flat pieces do you have? And then surface area of a prism, well, we got one base, so we find the area of that one base, and you add it to half the perimeter of the base times the slanted height. And it's slanted height because a pyramid is slanted. So it's the slanty height, not the straight up and down height, which is slightly different. And then to find the volume, we got 1/3 the area of the base times the height. So, I mean, kind of if you think about a cone or a cylinder with a cone cut out of it, you have the two sides that go away and you're left with 1/3 of it. So kind of that makes sense, I guess. And then surface area of a sphere is 4 pi r squared. So it's kind of like area of a circle, but there's more of them. Like there's 4 of them. Kind of makes sense. And then the volume is 1/3 of that, so 4/3 pi r cubed. And remember, volume should always be cubed. So I know these look similar, but area is always squared, volume's always cubed. Sorry that was real long. And there's still more. Like I could talk, there's so many circle theorems. Like too many. And there's all this trig stuff too. Oh my word. Like I could just, there's so much. Actually, like now that I'm thinking about it, do I want to share anything else about like trig? I guess we did our like whole trig unit. Yeah. Midpoint and distance. Midpoint and distance. There's a midpoint formula. It's like x plus x over 2, y plus y over 2. You're literally just finding the average of 2 points. Add them up and divide by 2. That's what a midpoint is. It's the middle. It's an average. And then the distance formula, you know, there is a really long distance formula with like a big old square root and a bunch of x's and y's in there. It's basically the Pythagorean theorem. So like c equals the square root of a squared plus b squared. But if we're in the coordinate plane, I just think of it as rise squared plus run squared. Because if you're finding distance in the coordinate grid on a diagonal line like this, I'm just making a right triangle. Like I'm drawing my little rise run right triangle right here, and I'm just doing rise squared plus run squared to get that hypotenuse squared. Sorry if that's wild. Okay, I'm gonna stop this now.